question, we have 4 1-gram spheres, so 4 spheres. They're released simultaneously and they're allowed to move away from each other. So initially they're all at rest, then we let them go and they start to move. What is the speed of each sphere when they are very far apart? So each of these spheres has the same amount of charge. They each have 10 nanocoulombs. They're all separated, each corner is separated by 1 centimeter. So this is going to be an energy problem. So initially they're at rest, and in the final situation they've moved away. So if we were going to sketch out a picture, we would start with our 4 spheres right here. So initially they're at rest. As soon as we let them go, they will start to move. And then our final case is they're very far apart. And by very far, we mean approximately infinity. Far enough so that the distance is really big. So let's decide on our strategy. We know initially they're all close together and not moving. When charges are close together, they have potential energy. So let's set this up as a conservation of energy problem. The final energy of the system equals the initial energy of the system plus any work done by non-conservative forces. A work done by a non-conservative force is equal to work done by something like friction. We don't have any friction or anything in this problem, so the work done by the non-conservative forces is going to be 0. So now, why don't we figure out what we're going to write down for our final energy? Why don't we figure out what we'll write down for our initial energy? We'll set those guys equal, and then we'll figure out what the final speed is. So for our initial energy, the 2 kinds of mechanical energy we can have are kinetic and potential. And in this problem, it's electric potential energy because we have electric charges interacting. So kinetic energy has the equation of 1/2 mv squared. These charges are initially at rest, so our initial kinetic energy is 0. Then our initial electric potential energy is, we have to think about what's the energy of interaction of these charges. Well, if we look at it, each charge interacts with all the other charges, so we have to add up each interaction. So let's start off by numbering each of the charges. So this will be charge 1, charge 2, charge 3, and charge 4. There's our charges. So our energy of interaction will be the energy between charges 1 and 2 plus the energy between charges 1 and 3 plus the energy between charges 1 and 4. Okay, those aren't the only interactions. 2 also interacts with the other charges. We've already got the energy between 1 and 2, so next we'll write down the energy between 2 and 3. And we need the energy between 2 and 4. And last, we'll add in the energy between charges 3. So charge 3 interacts with 1, that's this energy. 3 interacts with 2, that's this energy. 3 interacts with 4, so we'll write that guy down. And then 4 interacts with 1, we've got that term. 4 interacts with 2, we've got that term. 4 interacts with 3, we've got that term. So we've written down all the different possible interactions, 1 due to each charge. So electric potential energy in general is K times Q1 times Q2 over the distance between the 2 charges. So let's see how we're going to write each of those down. So the energy between 1 and 2 is K times Q1 times Q2 divided by R12. R12 is the distance between charges 1 and 2. By comparing with this picture here, we see that R12 is 1 centimeter. For the sake of simplifying the analysis of the algebra, I'm going to leave this as a symbol for right now. I'm going to call that distance D. So I'm just going to label that D. It's just going to make it a little bit easier to simplify. If you don't like working in symbols, you can of course put numbers in and you'll still work the problem out, but you'll see that it simplifies a bit as we go through. Q1 and Q2, all of these charges are the same. So Q1 equals Q2 equals Q3 equals Q4, and I'm going to call each of those guys just plain Q. So our energy of interaction between charges 1 and 2 is going to be K, Coulomb's constant, times Q squared divided by D. So there's our energy between 1 and 2. That's what I'll fill in this step. Okay, next let's get our energy between 1 and 3. That's K, Q1, Q3 divided by R1, 3, the distance between 1 and 3. So this distance is also D. So that's going to give us K times Q squared over D. So we see already that these are going to be easier to add up if we leave them in symbols first. And then the energy of interaction between 1 and 4 is K times Q1 times Q4 divided by R14. R14 is the distance between charges 1 and 4. So that's from here to here. So if we wanted to compare with this picture, between R1 and 4 is the distance from here to here. This is the hypotenuse of a right angle triangle. This length is D squared plus D squared. So that would be root 2D. And root 2 times 1 centimeter is 1.41 centimeters. Again, if you wanted to put your numbers in here, no problem, you absolutely could. So that's equal to root 2 times D, or 1.41 centimeters. So now we've got K times Q squared over root 2 times D. Okay, next let's get the energies of 2 and 3. U, E, 2, 3, so the electric potential energy between charges 2 and 3 is K times Q2 times Q3, got to make sure we get all those symbols right, divided by the distance between 2 and 3. I won't draw that on this diagram because it's getting a bit full up. So the distance between 2 and 3 is from here to here. That's also the diagonal of that square. So that's also root 2 times D. So KQ squared over root 2D. The energy of interaction between 2 and 4 is K times Q2 times Q4 divided by the distance between 2 and 4. So there's our 2 and 4. That's the same as D, that's also 1 centimeter. And so that's going to give us K times Q squared over D. And then the last one we have is the electric potential energy between 3 and 4. So that's K times Q3 times Q4 divided by the distance between 3 and 4. The distance between 3 and 4 is 1 centimeter. So we've got K times Q squared over D. So our total electric potential energy that we'll fill in for our initial mechanical energy will be the sum of all of these guys. So why don't we write that part out next? I'm going to grab a fresh sheet of paper here. So, let's see. So our initial electric potential energy then, UE initial equals, we're going to sum up all of these terms here. So K times Q squared over D plus K times Q squared over D plus K times Q squared over root 2 times D plus K times Q squared over root 2D plus K times Q squared over D plus K times Q squared over D. Now, if you preferred numbers, you probably have a number worked out for this already. Why don't we simplify a little bit by taking KQ squared over D outside. Let's see what we get next. So that's K times Q squared over D outside of 1 plus 1 plus 1 over root 2 plus 1 over root 2 plus 1 plus 1. Okay. And then that simplifies down to K times Q squared over d times 1 plus 1 plus 1 plus 1 is 4. 1 over root 2 plus 1 over root 2 is 2 over root 2. So at this point, if you wish, you could put your numbers in. If you put your numbers in, you get 4.867 times 10 to the minus 6 joules. I'll hold off just yet because I'm not quite ready. So now my initial mechanical energy, E initial was our initial kinetic plus our initial potential, equals K times Q squared over D instead of 4 plus 2 over root 2. For our final mechanical energy, E final is equal to K final plus U E final. So what are each of these terms? So K final, we have 4 charges and they're moving. So K final is K final of 1 plus K final of 2 plus K final of 3 plus K final of 4. So that's 1/2 times mass 1 times velocity 1 squared plus the same equation for each of them. Now, we know that the masses are the same. Each of the masses is 1 gram. And then by the symmetry of the problem, because they're all arranged on a square, by the symmetry of the problem, they'll all have the same final speed. They all experience the same force because all the masses are the same and all the charges are the same. So if we add up a half, so M1 equals M2 equals M3 equals M4, and V1 equals, so we can call all of those guys M. V1 equals V2 equals V3 equals V4. We can call all of those guys V. So we'll add up all these guys, a half mv squared plus a half mv squared plus a half mv squared plus a half mv squared. It's going to give us 2 times m times v squared. So there's our final energy. Our final electric potential energy would still be the interactions between all of them, but remember, electric potential energy is K Q1 Q2 over R12. The charges are far apart. If they're very far apart, then R12 is a really big number. This is a really big number. It means that the electric potential energy is K Q1 Q2 over a big number. It's about equal to 0. So let's put these in for our final mechanical energy. We'll set them equal, and then we should be able to solve for that speed. So K final is 2 times m times v squared plus 0 for our final potential equals 2 times m times v squared. Okay, now we're good to go. We know that E final equals E initial plus any work done by non-conservative forces. And we already said that the work done by the non-conservative forces was 0. So E final equals E initial plus work done by non-conservative forces like friction, of which there is not any. We'll put in for our E final that it's 2 times m times v squared equals our E initial, K times Q squared over D times 4 plus 2 over root 2. Now the numbers that we have to put in here are that the mass is 1 gram, the charge Q is 10 nanocoulombs, D is the distance, the length along one side of the square, that's 1 centimeter, and K is our Coulomb's constant. So we can solve for our V, divide both sides by 2m, and take the square root of both sides. And what we get for our V is 0.0 493 meters per second, or 4.93 centimeters per second. So that's how far away they'll be once they get apart from each other, once they escape.